All right, I'm hoping that the people who are here, most of them went to Todd Cooper's presentation yesterday morning. We're talking about devices in general, medical devices that is, and the representation of device data in fire. That was an overview, and there were a lot of different standards and specializations involved. In this particular case, what I'm hoping to do is to actually dive in and do some work, and I'm going to try to lure all of you people into a developer's session where you actually do some coding. And this particular use case is for a special subset of devices known as personal health devices. Personal health devices are cheap relative to hospital devices or POCDs, point of care devices, usually afforded by the consumer, and it also tends to be used by patients versus medical professionals. The nice thing about them is relative to the other sets of devices, they are the simplest. And if you want to start learning how to work with device data and dealing with fire in general, this is a pretty good place to start, as it is the simplest possible one to do. It's actually been done in practice, so we have some experience behind it. But one of the things I want to do here first is to demonstrate what I would like you to do. So I'm going to hop out of this title screen, if I can figure out how to do that. If you get more than anything out of this, I want this to be done. What I have here is, and what I want to give to everybody is a simple Java project. All right, runs. I've got an IntelliJ project. You can modify it so that it goes in Eclipse or whatever other Java tool that you have, and you're going to take this code and play with it, make something decent out of it. All right. So what the PhD implementation guide profile does, it explains how to take PhD data, and I've got a bunch of them up here, and I'll have these things to play with. To take that data, a gateway will communicate with it. In this case, it's on this phone, and you can see it over here on the side. I've got Droid at screen showing it over here, if I can see my mouse. Yeah, okay. And you take a measurement, the phone decodes it, the gateway then converts that data into fire, following the PhD implementation guide, and uploads it to a fire server. And that's basically where it stops. And the whole concept here is the PhD, like the POCD and the other types of devices, represent the data in the same way, so that we can have a consistent representation of the PhD data as to POCD and all the other types of data. Now, what I'm hoping to get people to do is to develop an application or to play with an application that reads that data. There hasn't been so much work done on that, and I'm pretty lousy at doing that aspect of it, but I'm hoping there's some geniuses here who are better at that. And over on this side, I have a basic project which did the dirt work so that you wouldn't have to do it, because if you had to do that before you ever had a chance to do anything fun, the time would be out. I suppose one could argue, oh, how about on the device side? Well, the problem with the device side, understanding the device protocols is pretty important to understand how to work with devices, and that's not something you're going to learn in 3 days. It just simply is not going to happen. I should say our extra scheduled sessions for development, we had one yesterday where people come. There's one this afternoon, and there's one tomorrow, and they're in the Oprah room. I think it's at, what time is it? It's 2 o'clock in the afternoon, is it? At 2 o'clock this afternoon? 5:30 or something. Oh, to 5:30? Yeah. Okay, so, and tomorrow morning. We will be there if no one shows up. Well, I hope that's not the case. And this project is available now on the FIRE website under the devices track. You can download a zip file which has it in it. So we can start with that and make life a little easier. Now let me explain what this project does. And I should say, James Agnew will be there to help you with the Happy Fire, because the project uses Happy Fire. And if you just want to learn how to use Happy Fire, this is also a good exercise because it's a pretty simple way to do it. Now, what the project does, it does the basic dirt work. It sets up a subscription to subscribe to any observation that references a certain patient. And so when I upload from this device or from the gateway an observation that references that patient, this application will get pinged that that happened. And so at that point, you have to do some work. The application goes and gets the resources that caused the ping. So it downloads, gets the observations. Then it looks inside the observations and says, okay, which device resource was responsible for it and which patient, and it downloads those and displays them. That's all it does. So the point here is that we're going to take the implementation guide, take this program, and you're going to learn how to get the data for the PhD data out of the resources that are created. Fortunately, it's relatively simple. There are only 3 resources involved: patient, observation, and device. So what I want to demonstrate is how it works. Okay, so I'm going to take a device here. It's a thermometer, and I will take a measurement. And when you see that button up there clicking, the measurement has made a contact, it's connected, and it's been transferred. This device doesn't like to shut up, though. It takes about 40 seconds before it finally decides to disconnect. In the meantime, it's sending battery measurements over and over again. Don't ask me why. I don't even want to, don't get even started when it comes to the headaches of Bluetooth and other things like that. So when that is done, I will then upload it to a Fire server. Right now, it's a Happy Fire server, which is located in Virginia in the United States. It will come back here. This will ping this application on the right-hand side, on the left-hand side, and then I will go get the observations and display them, as well as the device information and the patient, in theory. Okay, it's ready. That blinking dot has stopped. And I have to admit that if you actually looked at it on the phone, it would be blinking like this, about 8 times a second. But what you see on the screen there is about once every or twice a second. It's some problems with it. Okay, so now I'm going to press that little cloud up there that says upload, and I've made it that way so I have time to do it. The Fire bundle response is successful. And as you see, it just spit out the junk over there on the other side. That's the cool thing about subscriptions. It's in real time. And it just makes any application that's kind of cool. So what I'm hoping you can do is take this project, which does nothing but those very basic things, and do whatever you want. Maybe make a simple remote patient monitor in the sense that pretend you're writing something for a doctor's office. And all you want to do is tell the doctor that there are patients out there have taken their measurements. And if they haven't, you've got to do something to make sure that they do, because you're monitoring them. Or it could be, for example, you're monitoring a pregnant women or something and looking for preeclampsia. And you detect when that condition has set in. And so you'll take measurements, and if the blood pressure, say, goes up or something else like that or whatever, then you know it's maybe time to do something about it. But that's the idea, whatever you can dream up with. So now I can stop with this, and in order to understand it better, I'm going to go and describe what we have and how it works. So now we'll go back to the presentation. There are any questions on actually how this worked? Does it make sense? Do you want to come and do it? I hope so. All right. If I fail to sell it, then that's my problem. What's that? Clear. Okay. All right. So let's get some idea of what this is. All right. So ideally, we have this dream of standards. And having been implementing on the upload side, this is really a dream. But this is the basic thing of what's going on here. Over to the far left, we see personal health devices. Now, wouldn't it be nice if it were such that you would buy any one of these PhDs and from any manufacturer, and they would work with any PHG gateway, that's what the G stands for, the PhD Personal Health Gateway, from any manufacturer, and they would work. That would be the case if devices followed a standardized protocol. Some do, most don't. And that, of course, is a headache, especially for us implementers, because if you want to deal with that, you have to write code for every damn device that doesn't follow a standard. Okay, and then at that point, the next stage is from the PHG sending the information to the FHIR server, the back-end server. That part, believe it or not, is a lot simpler. Of course, you have to map and decode the data from the devices, which is binary. And so that's always an issue. And you have to understand the protocols and the transport protocols in order to do that. And that's why I would say it would be very difficult to have a let's build session to do that part of a PHG. You're not going to do that in 3 days. Not a chance. That's something that's taken me months and it still doesn't work. And from that point, it gets up to the FHIR servers, and then we have a reader application. And that's what you're going to be playing with. You're going to be learning how to use this data, take the data from the observations and pull it out and do something with it. Something better than I can think of. Okay, so there has been an attempt, the PCH, Personal Health Connected Alliance, and now they're joining with IHE, to try to make this interoperability guidelines for the device all the way up to the back end. It would be nice and it would work if only device manufacturers would use it. That's a different problem. Okay, so what does exist out there in the software world to help you in this problem? Right now, Continua and PCHA is working on projects that you can eventually, hopefully, take and use it for production. What does exist now, there are applications you can download for the actual FHIR servers and for the modification of the device data to FHIR. What doesn't exist yet is the Bluetooth engine. And that's, of course, by far and away the hardest part of all of this. So when that's done and all of those are in place, maybe then we can have a let's build session for this. What is in place is the Personal Health Device Implementation Guide. Just last week, we got through the final stages of balloting, and it is now ready for publication. You will find it on the FHIR website, so but it'll eventually be one of the registered FHIR profiles. And it basically consists of 2 parts. Part 1 is the conversion of the PHG side, where it describes how to take device data and map it into FHIR. And I said this side is very difficult, and we had some major issues in balloting because the people who are reading it looked at that and they didn't understand the device protocols that were being used and the fact that there was binary. It says, what is this? And it was very confusing to them. We understood that we have to do something a little more than to describe just the mapping. So the mapping part is, we will ignore that for the moment. Let's go to the part 2. Part 2 describes, once it's in FHIR format, you don't have to know anything more about the device protocols and all these terminologies that are used in that. And that part is just for the consumers. And this is what we're going to work with. That's much more understandable. It's based just on FHIR, and you have to know very little information about how these devices work. And what I'm trying to tell you is, let's try and do this, take that project and write some code. We will provide you with devices, and we will provide you with PHGs. And if you happen to have Androids, you can get the PHG off the Android Play Store or whatever the hell, yeah. Or I can install it on your Android. That's usually probably the easiest way because it's more up to date. I'm fighting with Google Play Store right now. They won't let me update because I'm coming from a place that they don't understand. And they say, And I want you, in order to be able to do this, you have to upload it from a device that we know. Well, those are in the United States, so I'm stuck. I can't do much about that at the moment. So we'll provide this, and we'll provide that project. And you're going to can download the project from the DevDays website. And the two is the UDO. So as I say, how are we going to help? We're going to provide you with that basic project. And so that will save you a lot of spin-up work. It already works. It's nice to have something that works, because if you modify it and it doesn't work, you know, oops, I did something funny. And as I should mention, James Agnew will be there to help. So if you just want to also learn how to use Happy Fire, this is also a good way to do it. We've got a base project there working, and it's something practical, and you can understand how Happy Fire, how to use the Happy Fire project, because that's what this project uses. Not the gateway, but the example project. All right. In order to really go any further, you have to understand, what does a PhD, personal health device, what kind of data does it create? And in the end, this is what you get. We only use 3 resources, and this slide shows the relationship between the 3 resources. Most people are interested in the observation. And in the observation will have a field in it, the observation.device, and that will point to the actual device and the information about the device resource that describes what the PhD has. And then there will be a subject, and that's the patient. Now, I have to say that personal health devices have no patient information. So that must come out of band somehow. And in the IG, the implementation guide for this, the only thing that is required in the patient resource, should you choose to use it, is the identifier. And the identifier can be opaque. So in other words, that's a way to hide personal health information. And in many cases, you may want to hide personal health information, because what you're going to upload is sensitive data. On the other hand, you may want to actually display it, because what you're uploading is fitness data, and you want to brag to the world that I just ran 15 miles today, and so you put your name all over it so everybody can see it. So that's the other option. So that's, fitness data is out there. So we do not restrict the use of the name in exposing your personal health information, but we do not require it in the implementation guide. And in fact, there's another alternative. And that's what I like to call the Norway case, because they're the ones that insisted that we kind of have it. And that is where you give the out-of-band information to your PhD, the logical ID of the patient resource that's already up there. And that way, in that particular case, the PhD never generates a patient resource. It never has any information about a patient whatsoever on it. Almost like the perfect protection of a patient. And the only thing you have the patient, the logical ID on the phone for, is to stick it into the observations and other resources that need that. So that's another alternative. Okay. So this is perhaps the most important thing I want to tell you about PhD data, and in fact, everything when it comes to device data that we're doing, POCD and all the other things that Todd talked about. We are using a generic modeling approach. You wouldn't believe how many times this is not the way it is done. What is often done instead, and we see it everywhere, is that they'll make a unique structure for every type of measurement that you can think of. So, and usually it starts with something simple. Say, oh, let's take a temperature measurement. How can we represent a temperature measurement? That's probably the simplest measurement you can dream up of that comes from such a device. And they dream up of a simple structure, as small as possible. Then they say, okay, now we need to do blood pressure. Oh, everything I did for this, it's not going to work. So I'm going to have to create something new. So they create a new one. And then they look at, pulse ox. Oh, I need a new one. And by the time you get done, if you look at the mobile health, they have something like 1,000 different structures, and every one of them is different for the different types of measurements they represent. As an implementer, I would like to shoot them, because that means I have to, if I want to support everything, I have to write code for 1,000 different types of measurements and decode that. Now, of course, I'm a lazy programmer. I don't like that. This approach, and FHIR basically does the same thing, but this approach of having a generic model for representing measurements has been around for a long time in the IEE 11073 sets of standards. And what it does instead, it says, what types of measurements, what value types can these devices do? And they can only do 6, at least personal health devices. One of them is a scalar, a simple scalar. These are the ones that are most common. A temperature, a weight, a glucose concentration, how many miles I ran, all those kinds of things that can be represented by a single number. Every measurement that's represented by a single number is mapped to FHIR in exactly the same way. Doesn't make any difference what the measurement actually is, only that it is a scalar. A vector measurement is something like an acceleration, X, Y, and Z components, or the blood pressure, systolic, diastolic, and mean. Now, I'm not going to try to fight about whether or not the blood pressure measurement should have been a compound measurement or a vector measurement or not. Somebody long before me decided, yes, this is the way we're going to represent it, and that's the way it was done. You could easily split it up as you could split up any X, Y, and Z and put an X measurement, a Y component measurement, and a Z component measurement as scalars. That can be done. But if it is represented on the device as a vector, we send it that way. And every such measurement is done in exactly the same way. The other type of measurement these PhDs can do are codes. The measurement itself is a code. This is common for context measurements. When I take a glucose measurement, I might also want to indicate when I did it relative to when I ate. Am I fasting? Did I do it before a meal, after a meal, at bedtime, whatever? And so there's a few set of codes that you pick. If I run this meter, there is a set, okay, and you take a list, which is it? I did it at bedtime. And you select that code. And that measurement is just a code. And there's one specific way to map that. So every measurement that happens to be represented by a code, and there are quite a few of them, are always mapped the same way. The other type of measurement are events or states. And the easiest way to think about this is, say I have a monitoring application in a independent living facility. You want to check the state of the patient's room. Is the humidifier on? Is the temperature on, or is it off? Is the door open or closed? Is the patient in the room, out of the room? These are state measurements, and they often happen simultaneously. You want to check all of them. This is probably the most complicated measurement because HL7 has no way to represent such a measurement. It is unique to device measurements. There's no way to map this in HL7 or no way to represent it in HL7. So we actually had to develop a second code scheme to convert these state measurements into something HL7 could understand. This is the same for CDAs and for FHIR, and we use that. These measurements are not that common, so that's a good thing. And the other type of measurement are waveforms, ECG traces, for example. I've got one here that can take ECG traces, and you can upload those. And those type of measurements are strings of periodic data, and they can be a lot. For example, this thing takes 250 samples per second for 30 seconds, so we end up uploading something like 7,500 strings of data as a long period. Now, you could be really dumb and upload each one of them as an individual scalar, do 7,500 uploads to accomplish the transfer of the data. Not too smart. So everything that's every periodic waveform is always mapped in the same way as the waveform. The last one is a string, just a human readable string. Fortunately, this is very rare in PhDs because all the string gives you, it's a human readable string. It's it's not processable on machine. The only place it's actually used is in cardio PhDs for cardio equipment, and it gives like the name of your program. So you go to the gym and you say, oh, this program is called manual or fat burn or whatever else. And that's the only thing that might be used for. It's the only thing I know it's used for. But this is the idea, it's generic mapping. So there are only 6 different ways to represent every possible type of measurement a PhD can produce now and in the future, unless they change the standard.
Question about the difference between codes and event states.
Yeah.
It seems like, battery low would be represented as a code. How is it different than a coded observation?
There is always a conflict between that. But when you design the standard, we use these event state type of situations when the event states can be simultaneously, when it happens simultaneously. So that you get a battery low, for example, say this, I take this pulse ox, and the battery is low, and it can have poor signal perfusion, the finger might not be in right, and so all of those happen simultaneously.
Like a vector of codes.
It's an integer, which is 16 bits or 32 bits long, and each setting represents something. Now, if it is the case that each setting is mutually exclusive, that means no two could happen at the same time. You should not use that type of measurement. And some places, they do it in the specializations. That's bad design. In that case, they should have used codes. But when you can get them multiple at the same time, then you use these.
So thank you. And a follow-up, there's another code on each observation, which is what identifies the observation.
Yes, exactly.
Where does that guy come from?
That guy also, everything that this profile talks about, everything comes from the device.
So the device knows the LOINC code for what it's meant?
It's not the LOINC code. This uses the IEE 2060, 10101 codes, nomenclature codes.
So that's interesting. The relationship between what you're doing in US Core then must be fairly strained, since US Core is going to require LOINC.
Yes, they require LOINC, but this is an international standard. It's used in Japan, it's used in Korea, it's used in Europe, and Denmark is very strong behind it. I mean, the IEE codes, the MDC codes have been around for a long time. It is now part of the FIRE standard, so it is in there. And there is also a mapping that has been developed by the LOINC people to map MDC into LOINC for those that need it. Okay, so you will see that when we actually generate the observation resource, the required type code is the type code that comes from the device. It's just a number. It's a 32-bit number. And the reason for that is that I don't have to make any map on the PHG in order to do it. Now think of how remote patient monitoring works. I've got 10,000 patients scattered all over who knows where. And in every place, they have one of these PHGs. I want to make sure that when they get a new device, that I don't have to make a new map. Oh, geez. Or say a new specialization comes out. I don't have a map on this for all those new LOINC codes. What do? No good anymore? It's totally non-future-proof. So the whole concept of this is that the PHG does not have to know anything. It is pure dumb. All it does is take the structure that it gets from the device, uses that device information, and converts it to FIRE. Now, clearly on the read end, when you read those codes, you have to know what they mean. So when the codes get updated for a new device, then you have to do it on the read end. But for the PHGs out there in the field, all over the place, you don't. So that's a very important part of this generic mapping. All right, so what I wanted to take a little bit of look at so that you can understand some of my frustration is this is the part of the PHG, the Personal Health Gateway, what you have to do if you want to design a personal health gateway. And you can see over to the left all the different types of devices. What's the dream? The ideal one is the top, where every single device follows a specific standard. And the IE 11073 protocols do that. So if I have such a device like this guy here, and the USB one on this one, I can use exactly the same code to work with both of those devices. In fact, that code was written back in 2008. I haven't had to touch it since. New device specializations come out and they work. Future-proof, wonderful. Then along comes BTLE. And I could kick them in the butt a few times, but what they decided was to be more efficient. But in their generous thinking, they did not make any consistency between different device types. So they generated a specialization for all heart rate monitors, and another one for all blood pressure cuffs, and another one for all thermometers. And they're totally different. So you have to write code for each one. All right, there is an advantage of that over proprietary devices, which is the biggest nightmare, because every heart rate monitor from any company that follows that specialization, I can use the same code. But if they come out with a new specialization, which they do, my PHG out in the field is useless for that. I have to write new code. There's no way to avoid it. You have to write new code. Somewhere that code has to be written. So I've got a little arrows in there. And the worst is the proprietary device. You have to write special code for that device, and it works only for that device. So I put each arrow represents suffering for the PHG implementer. And I'd like to minimize the number of those arrows. All right, once we get beyond that, there's even more suffering because we have to decode this data and then convert it into FHIR. And when you have all these specializations, the top one is the easiest. You have one single file that handles it because it's a consistent way of representing the data. It's always the same. You don't have to worry about it. And again, I have one set of code that deals with it. That's not the case for Bluetooth Low Energy. I have to write a separate set of code to make the translation to FHIR for each of the specializations. And when a new one comes around, it's no good. And it's even worse for the proprietary devices because I got to do one for each one of those. And it may be the case that it's not even possible because the proprietary devices don't do certain things that you need to have done. All right, so that's just kind of my complaint about devices. And one reason why we're going to skip that aspect of it, because I think I remember here when we had our first DevDays, we sat around, people try to get their things to work with the devices all 3 days, and no one got them to talk to each other. It just didn't work. So let's forget that. That works now. But okay, so the final stage is to take those FHIR resources, which are only those 3 different resource types, and upload them to a FHIR server, and then the PHG implementation guide, part 2, the part that you're doing, you're going to read that and do something with it, whatever genius things you can come up and think of. Now, you might note up there, there's 2 devices. One is the PhD, these guys, and the other is this one. Why is the PHG even considered? Well, in most cases, it probably isn't so important and nobody's really interested in it, but it does play a role. Personal health devices, unlike 5,000 and 10,000 euro POCD devices, are kind of cheap. For example, there's not any one of the devices on the market that can synchronize to time. So the time can be completely out to lunch. You've changed the battery and it goes back to some factory reset back in 2007. Matter of fact, that's what will happen with this device. It'll be like October 1st, 2007. Well, that's a problem. And so it's the job of the PHG to fix that. And that is possible to do as long as the device keeps a continuous time clock. It doesn't matter if it starts at 2007, as long as the current time keeps moving on from that, the PHG knows what the current time should be, what time zone it is in. It also knows the time zone of the device because it's right next to it. These are local transports. So that's not a problem either. So what the PHG does is it reads the current time of the PHD at its current time and checks the difference. And if there is a difference, every measurement that is uploaded is corrected by that difference. So that's why it's kind of important to know what some properties about the PHG. What's its time synchronization capabilities and those kinds of things. All right, so I'll just skip this part. The implementation of a PHG is difficult, mainly because of the different types of things you have to know. You have to understand fire, which is a completely different type and nature of protocol than understanding device protocols, which are binary. Okay, I don't know if I really want to go any further than this. I think I've said the major things that I want to say. So let's just leave it at that. And I'll take any questions if there are any. And please come and write some code. Any questions? Okay. Oh, go ahead.
Yeah, so this is all Fire 4, right?
Oh, yes, right, yeah. It's kind of an interesting history behind that because it was when we first tried to do it in DSTU2, we had a very difficult time trying to represent PHD data in the device resource. We had the device and the device component, and some of the information was on the device and some of it was in the device component, and some of it didn't exist at all. Eventually what happened is we merged the two together and added the necessary support to represent everything, and we're very happy with R4 right now with the device, at least for PhDs, and we've got a lot of experience using it. And we hope it doesn't change, or if it does change, it doesn't change the fields that we need. So yeah, we use this is R4. Yeah.
What ballot phase are you in with the IG?
It finished, so it's ready for publication. It just finished last week.
Is it STU or?
Oh, we will. I think we're going to make it it originally was going to be normative, but the device resource is only at level 2. Even though the observation and patient are normative, device is only at level 2. And so it will probably be a DSTU and not a normative, though. Yeah, okay, another reason is right now the implementation guide doesn't support a UDI. And that's because there's no devices that support UDIs electronically. All right, everything has to be done here electronically. Go ahead, yeah.
So what type is the unit of the scale?
The question was, okay, I got 1 minute left. What type is the unit of the scale?
Yeah, so how do you store the unit?
The units, the quantity. Oh, that's part of the protocol. Believe me, it's part of the protocol. So I mean, everything you need to know comes from the IEE metrics, units, values, timestamps, type. It's all has to be there.
I think it's bound to UCOM, right?
The unit is also MDC codes, but we map them to UCOM. So what's displayed in Fire is UCOM. However, if you read the details in the implementation guide, it says specifically for to be future-proof, that if you don't know the UCOM code for the MDC code, use the MDC code, because the device, the PHG, will always know the MDC code because the device provides it. It does not provide UCOM. That's too inefficient. These are binary. Yeah, go ahead.
You said there is no support for UDI in the devices, but in your sample output also is some UDI.
Fake. It's all fake. It was doctored just because we wanted to demonstrate that the device resource, which has the UDI, that we can do that. But no, it's not. And in fact, there was something else, that the UDI profile in fire had to be fixed because there was no source that came from electronic source. They had human input, or there were a few choices. But no, this is going to be electronic from the device. So we had to add that, and that has been added. That'll be in 5, yeah.
One final question, I guess. You have some devices there. Can you say how many devices are now compatible with this approach? So that
Can I say how many devices are actually follow the standard?
Yeah.
Unfortunately, not enough. That's about the only thing that I can really say. Not enough. And especially when it comes to the 20601 standard, because that's a lot more difficult to implement, though it is also a lot more robust. If you want a device that's guaranteed to work, get one of those. But unfortunately, they cost. But they work. It's a much more robust and reliable protocol.
you've got some 6 devices there at least.
Yeah, I got more devices, but I only brought devices that follow specializations. Unfortunately, the market as it is requires that I have to sometimes map proprietary devices. I kick them in the butt, but I'm stuck with it. Yeah.
Are there any devices that talk fire directly?
No. The question was, are any devices that talk fire directly? That might happen in the future, but there's a problem. That's a lot more energy resource demanding. And the last thing people want are bigger devices that need more battery power, especially you have to wear it. You want the smallest thing and least obtrusive thing possible that takes the least amount of power so that your battery lasts as long as possible. Fire is huge, and compared to the binary protocols, it's disgustingly inefficient. Hopelessly inefficient. I mean, you got one line in there that takes the whole binary string. Is, you're talking bytes here, not kilobytes. That is a total different order of magnitude. But clearly, if you have a sensor on something like this, which people are doing, now you can, you've got wireless, you've got cellular, but these things are, power consuming compared to something like this, which is a glucometer. That's totally different. Okay, I guess I can't have any more questions. Or is that okay? Okay, we're done. Thank you.